Hi, my name is David Bergvinson, and for August 17th, 2021, we're introducing a new exciting tool to help us get ahead of food insecurity around the world. Last week, the IPCC introduced its assessment report, number 6, that highlighted the fact that weather variability is increasing due to our warming atmosphere. And the BBC highlighted this by calling it Code Red for Humanity, in which collectively we need to come together to reduce greenhouse gas emissions to reduce the pace at which temperatures in our atmosphere are increasing. We are very excited, though, to introduce this new index to help us translate all of this information into an actionable food security assessment tool that operates in real time. And so we've developed a dynamic Agro-Ecological Zone Index that will assess food insecurity based on the long-term normal conditions that are defining these agroecologies and comparing it to the current reality. And in given the IPCC's report on weather variability increasing, this is a very timely tool to help us. We break production into 3 categories: productive areas, suitable areas, and marginal production areas. We define these different areas based on the P over PT value, and also we use environmental triggers to start the growing seasons, such as a minimum temperature of 8 degrees Celsius and a potential evapotranspiration ratio above 0.5. For each of these 3 production zones, we have normal conditions in which P over PT is close to normal, a watch in which that value is between 0.1 and 0.2 below normal, and an alert when that value is below 0.2, below normal, and in the case of productive areas, a P over PT value is below 0.9. We find this is a very powerful tool, especially for tropical production zones, but it can be extended into temperate agriculture zones, especially when combined with soil data. So this gives us a global look at the different agroecologies around the world and the colors that deviate from the normal, showing either a watch or an alert for production. So as in the case of the southern part of Brazil here, for example, a watch because of the very dry conditions, especially for crops like coffee in this part of the world. We also see similar case for much of West Africa, where rainfall has been very good through most of West Africa, with the exception of some parts of southern Nigeria and Ghana, or Sierra Leone, for example. We see very good conditions through most of China, with the exception of the extreme northeast part of China that, again, below normal rainfall could lead to reduced crop production in this highly productive zone. Now we can zoom into different parts of the world. So in this case, we're zooming into West Africa, having a look at the very good production across all of West Africa, where the value of P over PT is close to normal. However, there are some places, such as Mali, where this value has been below normal, and this can have an impact on crop production and food security for approximately 900,000 people. Now, we can overlay this kind of tool with population density maps that can then relate this kind of weather insight to the population at risk. And so for food security, for a government or for development organizations, this can be a very powerful way of getting ahead of a humanitarian crisis and averting human suffering. We can also zoom over to the eastern part of Africa and have a look at Ethiopia and South Sudan. And here too we see that by and large production has been very good this year, with the exception of some high production zones that had below normal rainfall. This translates to impacting approximately 3.5 million people in South Sudan and 4 million people in the southern part of Ethiopia. This data set that we curate on a daily basis enables us then to bring together the key weather variables to generate a very accurate ratio of P over PT, and then compare that to the long-term normal. And when that difference is significant, such as the case here in South Sudan for a highly productive area, we can issue an alert, and we know how many people or what percent of the population is actually living in this area. In this example here, approximately 13%. And so, we can actually quantitatively assess the population at risk for each of these grid cells where rainfall has not met expectations and where crop production is likely to be below normal. If analytics like this are of interest to you, go to apps.aware.com where you can start your weather analytics journey. Until next week, take care.